If you attended SDS 2019, you might remember Vadym Mozgovoy from the University of Lausanne, as he won the Best Paper Award last year. Now he is back, and I'm curious to hear how he further developed his research on stress benchmarking using biosensors. The title of his talk is Exploration of Scenario-Based Simulations for Stress Benchmarking in Swiss Public Service. Vadym works with experimental data that consists of psychological and non-physiological signals of 18 Swiss public servants collected through wearable biosensors. He will show us how he uses numerical simulation to effectively identify workplace stress with a small data set. Vadym, welcome. I'll pass it to you. You have 15 minutes for the presentation, and then we can follow up with Q&A.
Thank you very much, Katerina. Good morning. My name is Vadym Mozgovoy, and I'm a PhD candidate from the Swiss Graduate School of Public Administration. I do a PhD in Public Administration. Welcome to the presentation on the topic exploration of scenario-based simulation for stress benchmarking in Swiss public service. The outline of today's presentation is the following. At first, I will describe background, research question, and experimental setting. At second, we will see problem representation, methods, and results. Finally, we will discuss findings and implications. Let me start with the background. Stress pattern recognition can be conducted at individual level, and it can refer to individual problem. At the same time, we can do stress pattern recognition at group level, and in this case, it will refer to group level problem or even organizational problem. For example, when stress index increases simultaneously for multiple individuals in the workplace, it may be a sign of organizational problem. However, it is difficult to interpret group level indices on stress. For example, suppose that on the right-hand side, you see a group level of stress, a group index of stress. In this case, we don't understand whether it corresponds to the high levels of stress or to low levels of stress. And we don't understand whether we need to worry about this level of index. In general, group level dysfunctions can be reflected by group level indices, and they can be accompanied by thresholds. For example, on the screen, you see a group level index of influenza. And this index is complemented by thresholds showing medium intensity level, high intensity level, and very high intensity level. However, for constructing of such thresholds using data only, we need a large and representative data set that represents very well small seasons and high seasons. If we don't have such representative data set, this is a problem for constructing such thresholds. Nevertheless, in such case, we can use numerical simulation approach for construction of benchmark curves. Now, let me describe you experimental setting. This research involves 19 public servants from Swiss Municipal Fiscal Administration. It is conducted from the 1st of November 2019 to 19th of December 2019. And employees work in the work environment with variable work intensity. They have bigger work-related stress in December than in November. During the experiment, employees use wearable devices that you see on the screen, and they have personal biofeedback on the smartphone. In parallel, information system registers response to stress in form of physiological and non-physiological signals. And now let us talk about the problem representation. I will skip some technical details and focus on the most important aspects. Here we have physiological and non-physiological signals. We transform those signals into features and we classify them into 3 stress-related states. First state is state of relaxation, that is denoted by R. Second state is the state of arousal, denoted by A. And the third state is the state of over-arousal, denoted by O. Further, we represent our data set as sequential realization of stress-related states over time. For example, on the screen, you see that the state of relaxation at time point T3 transforms into the state of arousal at time point T4. And it corresponds to the first order Markov process. Accordingly, from this data, we can say how often one state transits into other possible state. In other words, from this data, we can extract state transition frequencies and state transition probabilities. Now that we have represented our data in terms of first order Markov process, let us talk about methods for construction of benchmark curves. At first, we will formulate assumptions for high and low stress scenarios. At second step, we will support our assumptions with the data. For this, we use block resampling and distributions of state transition frequencies. And finally, we will simulate benchmark curves using Markov chain models. At first, let me start from formulating assumptions for scenario of high stress and for a scenario of low stress. For the high stress scenario, we assume that individuals are more often in the state of over-arousal. And we assume that they are less frequently in the state of relaxation in respect to some neutral state. It means that we want to upweight frequencies that are linked to the state of over-arousal. And those frequencies are denoted as high-frequency links. At the same time, we want to downweight the frequencies related to relaxation. They are denoted as low-frequency links. And the remaining links we want to keep just on average. So they describe some neutral state of the stress. And for the low stress scenario, we assume exactly the opposite from the high stress scenario. However, now we need to define what does it mean to have a low frequency link and what does it mean to have a high frequency link. And for this purpose, let us use the distribution of state transition frequencies for the all possible paths that we can have in our model. Now let us look at our data set. Our data set corresponds to the inhomogeneity regions of low stress work activities and high stress work activities. We can further split our data set into 4 blocks, block 1, block 2, block 3, and block 4. Then we do a resampling from those blocks. So it is called block resampling. And out of this process, we can extract distributions for each state transition. For example, On the screen, you see a state transition distribution from R to R. This is absolute frequency distribution. And you notice that this distribution is in fact a mixture of distributions that corresponds to the data pattern of low stress work activities and high stress work activities. As a result, we define high frequency as a 0.75 quantile of overall distribution and low frequency as 0.25 quantile of overall distribution. And then we verify this definition for other state transitions that we want to modify according to our scenarios. Now we have everything to complete high stress scenario and low stress scenario with the absolute frequencies. We simply replace low frequency with 0.25 quantile of corresponding distributions, high frequency with 0.75 quantiles of corresponding distributions, and the rest of parameters are averages of the distributions. But those are absolute frequencies. Now we need to transform absolute frequencies into probabilities. And for doing this transformation, we use a normalization trick. And by doing this, we get a state transition diagram for a high stress data generating process. And another state transition diagram over here for low stress data generating process. And now let us, we have everything to do numerical simulation because we have data generating process for low stress and data generating process for high stress that are typical for this work environment. Let me skip technical details about initial settings of parameters for doing numerical simulation. The most important here that each dot over here express them over arousal counts for group of users on average during specific day in the specific work environment. Further, we may overlay smoothed curve over here, and we can create confidence intervals. Confidence bands will express our uncertainty about data generating process. And further, we have incorporated our prior beliefs about data generating process in this benchmark curve. Same we do for the low stress scenario. This is blue curve that is over here. And finally, we overlay over arousal index. That is the counts of over arousal episode that on average a group of users experience during specific work day. We can also correct for the non-constant composition of users and non-constant hours of use if it is necessary for our data set. And now let us talk about the findings of this work. This research makes a contribution to methodological knowledge. It confirms a possibility of stress pattern recognition at group level, which may be a team, a department, organization, and at second, it demonstrates a new application of Markov chain modeling for simulation of stress-related benchmarks. And finally, it demonstrates a new methodology for constructing stress-related benchmark curves with limited historical data set in several steps. for constructing of benchmark curves, we proceed as following. At first, we need to train machine learning algorithm. This algorithm recognizes stress-related states. It can be, for example, Gaussian mixture model or another algorithm with another stress-related states. At second, we represent a problem as a Markov process. At third, we formulate assumptions for high and low stress scenarios. We can further support our assumptions with the data. For this, we study distributions of state transition frequencies, and we estimate parameters from those distributions. And finally, we can simulate benchmark curves from data generating process of high stress and data generating process of low stress. And in the end, we can overlay stress related index using data aggregation and introducing weights for correcting for not constant number of users per day and non-constant hours of use. And now let us talk about practical implications. Benchmark curves for stress-related index may serve to interpret and analyze group-level stress-related indices. It serves to compare stress levels across different organizational units. It helps to support stress prevention. For example, we can support blinded and anonymous group-level stress monitoring and support the development of new human resource management practices, occupational health and safety policies. Finally, we can identify when stress becomes an organizational problem. It includes the support of decision-making on stress management, the monitoring of the efficacy of stress management practices and interventions, and measuring the performance of stress management trainings. Thank you for your attention. I will be happy to answer your questions.
Thank you, Vadym, for your presentation. Let me remind the people in the stream that they can ask any questions at any time, and we will pass them through them to the speaker. I think we already have some. Okay. Do you use the numerical simulation to find the threshold instead of having that from the data?
What happens is that I use the data and I use the data-driven numerical simulation. The problem is that my data set is not representative enough for high and low stress levels, because I have around 2 months of data. This is very much a typical problem with biosensors, because usually interventions in the workplace are short-term or mid-term interventions, and users don't use the devices forever. This method allows me to integrate my assumptions about data generating process together with the data set. And my data set allows me to confirm to a certain extent my assumptions.
Right, makes sense. Do you have any empirical data from the lockdown period? It would be interesting, right, to see if there are any differences, for example, from home office or anything like that. Do you have any empirical data?
Empirical data from what period? Sorry, I don't hear.
From the lockdown period now.
From the lockdown period during COVID.
Yeah.
No, we didn't do the experiment with biosensors during COVID period. but it would be interesting, of course, this data.
Would it make sense to now validate the model with a new data set? Like now that you have the model and you would get now new empirical data, could you validate then that the model represents now this new data well?
Yes, from my perspective, it makes sense to validate the model and to construct benchmark curves together with group level index at one hand side, and on another hand side use some alternative measure of stress in the work environment. And for example, do a convergent validity test or a cross-validation. It would be interesting, yes.
Okay. Good. Thank you. Thank you for joining today, and most probably we'll see you next year again, I hope.
Yes, thank you very much. Thank you for your attention.
Thank you. Thank you, Vadym.